Uh, so like I said, promised you last a couple of times ago, what I was going to tell you about today was kind of like the singular value decomposition, because first, like it's a usual result involving matrices, and also because once you have the singular value decomposition, you can kind of like see that this alternative definition of the rank that I gave for a tensor coincides with the usual rank definition of a matrix, sorry, with the usual definition of rank for a matrix. So just to kind of maybe start with that, um, so let's talk about the rank. So if you think of the matrix as being like of size n by n, right? Well, this is a bit annoying with the conventions for the size of a matrix, right? But you know, when you do the matrix multiplication by a vector, right? For this to make sense, the vector has to have size n by 1, right? So actually, if you think of the matrix as a linear map or like as a function, you know, then the matrix, in fact, you know, as a map, what that means is that the matrix, its vectors in Rn and spits out vectors in Rm, right? So it's kind of like the you know, the size scopes are flipped, you know, because like the domain has like dimension n and the codomain has like dimension n. Now, so here's like the vector v, which has size n by 1, and it produces a times v, right? So there are many definitions of rank. Like the one that kind of like is useful to, let's see if this is recording. Yeah, the one that I'm going to think about for like the rank of a matrix is that, you know, once you have like the matrix from this perspective, then, you know, here's like Rn, here's Rm, right? So you have a vector v, it produces A times v, and the idea is like, you know, and they're kind of like vectors on Rm that are in the image of this map, okay, and that's called the range, right? So this is called the range of A. And the idea, like the traditional definition of the rank is that it is easy to show that this is like a vector subspace of Rm, right? Okay, it's a vector subspace of Rm, and because it's a subspace, like, you know, you can find its dimension and the rank of the matrix, and like, you know, the traditional definition for the rank would be the dimension of the range. Okay, so the rank of A, I'll call it Rk of A, would be the dimension of the range of the matrix. So that's going to be a number, right? The thing about the rank, which makes it so nice, is that it happens to agree with the rank of the transpose. Like there's so many alternative definitions for the rank that makes it like a very useful number. But you know, from our perspective, one way that to think about it, to connect it to the rank of a tensor is like, you know, thinking about it as being the dimension of the range. Okay. That being so far so good, hopefully it looks familiar. Now, what from the tensor perspective, right? As a tensor, like the thing that we had talked about is like if you think of the matrix, like, you know, the matrix A, you know, has two indices, right? Which in our notation, like, you know, we sometimes like are writing this way. So from our perspective, the matrix is a tensor of order 2, right? It's an order 2 tensor. So a matrix. So as a tensor, like there was the definition of tensor rank that I had given you, which meant the following. So the rank of the matrix as a tensor, let's call it TRK for tensor rank, right? So it's the smallest number, right? R for which Right, so the idea is that, well, let me call this like another index so that it doesn't get confused with the I or J on the matrix. So the idea is that, you can take tensor products of vectors, right? When you take tensor products of vectors, there is like a natural way that gives you a matrix. So if you can find like a combination of tensor products that adds up to the matrix, that the smallest not combination, that's the smallest number of summands for which that is possible, that is the tensor rank. Okay, so it's the smallest number for which you can split up the matrix as a sum of like individual tensor products. Okay. And the thing is, like, from that definition, it's clearly not obvious that why that would agree with the typical definition for the rank of a matrix in terms of like the dimension of the range. Okay, so it's kind of like useful to see why these two numbers coincide. Because like the proof like goes through the singular value decomposition of a matrix, which, as I was saying, is a useful thing to know just in general. Okay. So for today, what I kind of will try to explain is why this tensor rank equals like the traditional rank of the matrix. Which, when in the case of rank one, we got kind of already discussed, right? For rank one, there was like this assignment problem that if the matrix had rank one, if you remember, if you remember the assignment, I mean, I left one of those as an optional question, right? But in the assignment, we had shown that if A was the tensor product of two vectors, right? Which again, from in our notation, I guess it would be something like this, if you transpose it, right? Because this is 10 by 1, and then the matrix had rank had rank 1. I think that's what I had asked you to show, but like the optional part of the assignment was like the converse, right? That if A had rank if A had rank 1, then you could find two vectors for which this happens, right? Then you can find for which A equals U and for B. So at least when I'm clearly 1 is the smallest number for which you get like at least you need a summand, right? Like so at least that does show that the tensor rank and the rank do coincide in this case. So at least in case 1, like at rank 1 is kind of like we already have a proof, but you want something that kind of like works in more generality, not like not case by case. So like that's what the singular value decomposition does. Okay. So the SVD, which is how that's called, let me write it down. The singular value decomposition. It is like a particular kind of matrix factorization. Okay. So it's like a type of matrix factorization. And like if you took linear, you would have taken linear algebra, but like in linear algebra, at least you do see some types of matrix factorizations. For example, the matrix happen to be square, right, and diagonalizable, right? If here's some examples of factorizations. If A was square and diagonalizable, then you basically, well, like depending on how you define this, you could define this to mean that it has its eigenvectors form a basis for the space, but regardless of how you want to write it, like the point of the diagonalizable matrix is that you can find an invertible matrix and a diagonal matrix. That's like where the diagonalizable comes from, or like the matrix is expressed as the product of these three matrices. So it's kind of like a factorization. And then like another one is that if A, which is like even better, you know, if the matrix has to be symmetric, right? Which only can happen if it's square anyways. So if the matrix is symmetric, then the diagonalization can be improved, because then you can take the matrix, this matrix P, to be, you know, orthogonal. Orthogonal, if you have not seen that before, is that it's more or less like a rotation matrix with some reflections. Like the determinant doesn't need to be necessarily one, but here like a R times R transpose equal to identity. Okay, and this is called like the spectral theorem. And that's in a sense kind of like almost like the best type of diagonalization you could get, because like the spectral theorem comes like with very nice properties. But if you notice, like both of these kinds require like a square matrix, right? One of the cool things about the SVD is that it can be applied for a rectangular matrix. So in a sense, that is better, like because it's like a little bit more broad. Okay. Okay, so the SVD can be applied to any rectangular matrix. Um, yeah, at least I guess I could write what it's going to look like. So like what is going to happen is that you're going to have like an n by n matrix, and you're going to break it apart into a product of three matrices. Okay. Let me just get the numbers right. It's going to be n by n, it's going to be n by n, and this is going to be n by n. Okay. And then I'll tell you soon what each of these matrices stand for. But this is usually how the SVD, factorization is written as. And I'll explain soon what U, sigma, and V are. Uh, but once you see what they stand for, you will see it's kind of like more or less clear, like how this connects to this tensor rank thing that I was saying a bit earlier. Okay. Yes.
What's the ID there for a model?
Oh, the ID means here like the identity matrix. So like like a rotation matrix, like, or like an orthogonal matrix, is one where if you multiply by its transpose, it gives you the identity. Another way of saying that is like the transpose equals the inverse of the matrix. That's an equivalent definition of being orthogonal. Um, but it kind of like looks nicer this way. Another way to think about it is that the vectors, if you think of the rows of the matrix, they are kind of like orthonormal vectors. When you kind of work it out, they end up having that property. But yeah, like in the symmetric case, it's kind of like nice, because that essentially what it says is like the matrix is roughly like a rotation followed by a rescaling followed by a rotation, like in a sense, like I mean, again, reflections are allowed, but yeah, that's roughly what's happening there. Okay, so again, like my starting point, I will only use. I do need to use a couple of things from linear algebra. So my starting point will be that I have this square matrix, right? So A is going to be n by n, which I was saying a couple minutes ago, one way to think about it as a map. So as a map, what that means is that A eats vectors in Rn, right? And it produces vectors in Rn. Okay. Now there's like this important result in linear algebra, which is like only the rank nullity theorem, that says that the which I'll use in a moment, you'll see. Just says that n, which is like the dimension of the domain, has to be the dimension of the nullity of A. Or is that the null space? Like sorry, like null space is like the name for the vector space and the nullity so like the dimension of the null. They usually people call it the kernel, so I'm more used to that name. The null space of A plus the dimension of the range of A. And the null space were just like the vectors, like when you multiply the matrix by that vector, gives you the zero vector. Okay. Such that A times B equals the zero vector. So the solution to the homogeneous system, right? Like that's one way to think about the null space. Okay, so the first thing is actually to do like a cool trick, which is like, okay, I start with the matrix A, which is not rectangular. Sorry, which is rectangular, so it's not square necessarily, but it is convenient to work with square matrices. So whenever you have a matrix which is rectangular, there's kind of like a couple of square matrices you can produce out of it. So the first step is that you're going to consider this matrix. I'll call it G. A transpose times A. So let's think about this matrix for a second. Yes, like this is the one I'm going to. So again, A was n by n, right? And when you transpose it, you flip the sizes. So this becomes n by n, sorry, n by m. So definitely you can multiply them, right? And you end up getting a square matrix of size n by n, right? I'm calling it G because usually this is related to what's called like a gram matrix. So which is what you could call it like a okay. So it is a square matrix, right? But it's even better than a square matrix because it's symmetric, right? Like that's the first thing that you can see. So right, what is notice that G transpose, right, is A transpose A transpose, and then if you remember how transpose works, like it reverses the order of the multiplication. But transpose equals A, right? So you get A transpose A, okay? And that's G again, right? So G is a symmetric matrix. Is that a thing? So G is symmetric. Uh, there's even okay. So what does a symmetric matrix entail? One of the things that it entails is that all its eigenvalues are real, so that it doesn't have any complex eigenvalues, or like well, all of them have imaginary part 0, right? So all the eigenvalues of the matrix G are real. Hopefully you did the part in linear algebra. I don't know if everyone covers that part, but it's one of like the more useful things that symmetric matrices have like real eigenvalues. But it's even better in this case. It's not only that they're real, but they're non-negative. So you can say even more. So in fact, they're all non-negative. So in fact, they are non-negative. Usually for like if that rings a bell, this type of matrix whose symmetric and non-negative eigenvalues is called like positive semi-definite. If for what it's worth. Not that you need to know the name, but if we talk about kernels and things like that, like a bit later, that is like a terminology that will come in eventually. But it's actually simple enough to see that the eigenvalues should be non-negative. Like it's like a quick proof that we can do. So why is that the case? Okay, because let's say that you have you just go back to the definition of like eigenvalues and eigenvectors, right? So if you have an eigenvalue and then a corresponding eigenvector, right? If lambda p are an eigenvalue, an eigenvector, then what does that mean? It means that G times B has to be lambda B, right? That's what it means to be an eigenvalue, an eigenvector for a matrix. But now you have to use the definition of G. So what is G? G is A transpose A times B equals lambda B, right? And then, I mean, this is like an equation. So you just multiply both sides of the equation by B transpose. So multiply both sides of the equation by B transpose. Like, let me put that in color. Okay, like it's a scalar, so you can move that, like, when you multiply both sides by B transpose, you can just put that scalar in the front. Okay. Right. So what's happening here? What happens with the right hand side? Maybe that's a little bit easier to see first, because V transpose times V is just like the dot product of V with itself. So it's the length of V squared. So that just gives you lambda length of V squared, right? And I mean, here you have to rearrange it a little bit, but it's kind of like the same because this is like, this would be kind of like A, B transpose just because of how transpose works. And so that gives you AB transpose times AB. So that's actually the length of AB squared, right? Right. So you get this is non-negative, this is non-negative, so that forces the eigenvalue to be non-negative as well. So lambda is greater or equal to 0. I should have deleted the red nullity, but that's fine. Lambda is greater or equal to 0. Okay, so that's great. It already tells you something about that's kind of you'll see that that's kind of like interesting information to have around. But okay, and then even something better happens, which is that the rank, and this is like something that's very useful to show. So again, like just to put everything back in place. So A was n by n, right? Which means that you can think about it as a map from Rn to Rm, and G, right? And G was A transpose times A, which is n by n, right? So you can think about it as a map from Rn into Rn. just to kind of like compare the two of them. Okay. So they definitely like, they start with the same domain, right? Like they have Rn as their domain, but they do land in different places because one has like, one lands in Rm, the other one lands in Rn, right? Now what if you apply the rank nullity to each of them, right? If you do rank nullity, this means that n was the nullity of A plus the range of A. Okay. And if you apply the rank nullity theorem to G, that will tell you that n is rank nullity is with the dimension of the domain. So that tells you that n would be the nullity of G plus the range. Well, sorry, not the range. Let's say the rank. I mean, it's the rank because it's like the dimension of the range. So we're dealing with numbers, sorry. So this is like the rank of A, and this one would be the rank of G. Okay. Now the cool thing is that despite the fact that they land in different, vector spaces in general, the ranks are the same. The ranks, they have the same ranks. What I'm going to do to show that is that I'm going to show first actually that the null spaces are identical. If the null spaces are identical, then these two numbers agree, and these like on the left hand side agree, and that forces like the ranks to be the same number. So it's kind of like a bit of an indirect proof, but it's kind of like interesting to think about it because like they do land in different spots. So what I'm going to show is that the null spaces have the well, I mean that they do have the same dimension. Well, I guess they're not. Yes, like they still can be thought of as being. They're not the same because they do land in different spots, but they do have like. But it's easier to. Let me see. Okay, so again, let's just kind of like useful to write down the definitions formally. So what is a null space? That null space were the vectors in Rn for which A times B gives you the zero vector. But I do want to specify that just to make it clear, like that there's no cheating. Like this is like the zero vector that lands in Rn. Okay. So I'm just going to put the subscript m to say that that's like the zero vector of Rm. And the null space of G, they are the vectors in Rn, right? Well, I guess yes, they will be the same sets, but like they do where G times E equals the zero vector, but this one is in Rn. So yeah, like both are subsets, both are subsets of Rn. It's just that if you want to do like a picture, like they may not coincide, but I'm going to show that they do. Okay. So, okay, so what if, let's prove like, how they're related. So what if you have a vector in the null space of A, right? What if, okay, let's start with the first one. What if B belongs to the null space of A, right? What does that mean? That means that A times B equals the zero vector with m entries, right? Well, just multiply both sides of the equation by A transpose. Maybe I should write G as A transpose, so just to make it more clear, that this is A transpose A. Okay. So, multiply both sides of the equation by A transpose. You can definitely do that because it has like the right sizes. Just do A transpose A times B it gives you A transpose the zero vector with m entries. That gives you the zero vector with n entries, right? Well, that tells you that V belongs to, that tells you that V belongs to the null space of G, right? So V, that makes sense? Okay, that works. And the converse, which is a little bit more interesting, is what happens if V belongs to the null space of G, if V belongs to the null space of G, if V belongs to the null space of G, that means that G times V would be the zero vector. But again, G is A transpose times A. This gives you A transpose times A times V equals the zero vector. Okay. And then now I do a similar trick to the one I did a couple of minutes ago with the eigenvalues. I just multiply both sides by V transpose. So that tells you that V transpose A times V equals V transpose times the zero vector. I mean, this is kind of like a dot. I mean, this is going to be a dot product. So it's going to be the number zero. So, okay, and that gives you, this is like the number zero, and that gives you the length square of A times V, right? So the only way for the length square of a vector to be zero is that if the number is like the vector itself, A times V is the zero vector. That's how norms work. So A times V has to be the zero vector. Which just tells you that V belongs to the null space of A. So it's kind of like an if and only if. If you belong in the null space of A, you are in the null space of G. If you are in the null space of G, you are in the null space of A. So they are really like the same set, and so they have their vector spaces, so they have the same dimension, so the nullities are the same. So once you know that the nullities are the same, if these two things are the same, that forces the ranks to be the same, which is kind of like actually what I wanted to show. And you'll see why in a moment. making sense so far. Let me summarize what we have then. So what I'm saying is that so far, I mean, may look a little bit weird, like why I'm doing this first, but now it hopefully starts to connect to the other stuff. So basically, just to summarize what we have done, you start with a random n by n matrix. So this is in general a rectangular matrix. Because it's rectangular, you want to kind of like produce something that's a square matrix. So an easy way to produce a square matrix is like just you multiply by its transpose, like A transpose times A. So this is like a square matrix, but it has like many useful properties, right? So like it was symmetric. Its eigenvalues were non-negative, right? Are greater or equal to 0. And the last thing that I just showed you is that it has the same rank as the matrix A. So the rank of G equals the rank of A. Maybe I should mention this. If you ever do least squares methods, this is like the normal matrix that appears when you're solving least squares. So like it is like an important matrix. I mean, this is like a useful thing that appears in many other places. So you'll see that this matrix pops out if you ever do like a version of like least squares, like and then you get like the normal equations and a bunch of other stuff. Okay. So, and then again, this was an n by n matrix, and now here comes like the fun part, because then you can apply the diagonalization for symmetric matrices that I mentioned at the beginning of the class. So just from the fact that it is symmetric, again, symmetric matrices can be diagonalized. And what happens in this case, because of some of these extra properties, is that, well, you will, because this is n by n, you will have n eigenvalues with repetitions included, right? So there might be repeated eigenvalues, but you can kind of like label the eigenvalues lambda1 up to lambda n. So let's call the eigenvalues. So again, repetitions are allowed, but because they're positive numbers, you can order them, right? Like, I mean, as long as they're real, you can actually order the eigenvalues, but okay. And then, okay, so you have those eigenvalues. So now, because they are non-negative, I can take their square roots without sweating it out. So I'll take the square root of each of these eigenvalues, and this is what is called like a singular value. So like the singular values are defined to be like the square roots, like the positive square root of these eigenvalues, which I'll call sigma I, or let's call it sigma k. So there's no they're not imaginary, there's nothing crazy because like the eigenvalues are non-negative. So this is totally fine. Okay, and then I will also again, because the matrix the matrix G can be diagonalized, you can find a basis of eigenvectors, because everything is symmetric, you can actually take them to be orthonormal. So then I'll also call B1, B2 up to Bn. Also B1, B2 up to Bn. is going to be an orthonormal basis of Rn of eigenvectors. There's going to be an orthonormal basis. Sorry, I'm not calling this, I should call them U1 up to. Sorry, U1 up to UN. It's okay. Now I should actually, let me see if I'm doing. No, this is fine. Let's see. Now I'm going to. I just hope I don't mess up the notation. So. Oh no, V1 up to Vn. Okay, yes, that's fine. How I had that before. Yeah, no, like this is fine. So this is an orthonormal basis of Rn. And the way I'm writing them, I'm thinking that V1 is like is an eigenvector corresponding to lambda1, V2 is an eigenvector corresponding to lambda2, and so on. Okay. So if you think about the vectors as scalar vectors, you can put them into a matrix, and I'll call this matrix B. And you'll see how it appears like later on. So this is a matrix. This is going to be an n by n matrix whose column vectors are this is a matrix B that showed up when I was writing that we were looking at a decomposition of G as, sorry, of A as, again, our goal is to write A as U sigma B transpose. So this matrix B is like the one that appears here, and the sigma matrix is going to be made out of the singular values. You'll see how that works in a moment. So the only thing that's kind of like left is to define the matrix U, and then we'll have everything in place to kind of like write down the singular value decomposition. Okay, so by the way, before we continue, maybe it's useful to kind of like think about how is it related to, if the matrix has happened to be squared, what's the relation between the singular values and the eigenvalues of the matrix A? So before we continue, just to see that first. So if A had been squared, just as an aside, well, how like, and if you have like an eigenvalue, right? And if let just to specify is like if lambda sub A had been an eigenvalue of A, let's see, so here, like I want to say that let's see. Oh, I think I have to also, let's just to make it easier, I think I also have to assume that A is symmetric. If A had been square and symmetric, let's say, just to make my life easy. Yeah, otherwise I don't think it kind of like super clear, like the relationship. And then that A had been an eigenvalue of A, right? Then that means that A times B would have given you lambda sub A times B, right? But yeah, then you multiply both sides by A transpose, right? Oh, this is just like the matrix G. But then if I assume that A is symmetric, right? This is the same as A times B if A is symmetric. And so that gives you another lambda sub A, right? Because this is lambda sub A times B. So that means that the eigenvalue square, would have been, so GB would have been lambda sub A square times B, right? So that means that if you square the eigenvalue of A, you would have obtained an eigenvalue of G, right? So would be an eigenvalue of G. And so like these singular values are just like the square roots of the eigenvalues of G. So like in this case, a singular value would have been, like the singular eigenvalue would have been like the square root of lambda A squared, which is just like the absolute value of like the eigenvalue of lambda sub A. So basically, the way you should think about the singular values is that they are kind of like the absolute values of the eigenvalues if the matrix that you started with happened to be symmetric. That's kind of like the idea. I mean, I guess you can reverse this to make sure that it kind of happens in general. But so that's how they're related to the case that if you had started with a symmetric matrix, how are the singular eigenvalues related to the eigenvalues of the matrix A? It's like it involves like it's just like they are their absolute values basically. Okay. What you going to ask?
I think that they have the same eigenvectors.
Well, this also would be saying, right, that this eigenvector would have also worked for G. Yes, like in this case, like that also says that. But then you have to check. You would have to think whether, right, if B were like eigenvector of G, that wouldn't tell you that B has to be like a vector of A, right? I think that is like a bit, more tricky, right? Like I'm not necessarily. I mean, like on the top of my head, no, I don't think so. But it is true. This is saying that you know.
But these here are coming from G.
Well, this V was I started with an eigenvector for A, right? So if I have an
I meant the B or P.
oh yeah, this right. I should have called them. Yes, in this context, right. This is just an aside. In this context, the V's are coming from G, right? Because G is the only one that's square, so in principle, so it's the only one that could have like eigenvectors, right? So even if both are squared, you do want to use the eigenvectors of G, not of A, if that's what you were asking. Yeah. No, I'm glad you asked me that, just to clarify. Yes. Okay. But the way, quick linear algebra question, maybe someone remembers this. How many non-zero eigenvalues does G have? Well, if the rank were n, right? But in general, right, like the rank may not be n, right? But I think you're heading in the right direction. That the number of non-zero eigenvalues is the rank.
Yeah.
Okay, right. Yeah. So this is why okay. So this is also the number. So the rank of A would be the rank of G, which should also be the number of non-zero eigenvalues. Non-zero. And that's why it's kind of like it would be useful to use that information. You see, like that's why I was trying to go over like the proof, that the ranks were the same, because I will connect that in a bit to the proof of like the decomposition. So that's another definition of the rank, which is kind of like more it's a number of non-zero, at least in this case, like when the matrix is square, right? Like okay. Whew. I think I have all these properties. Okay. So we're almost there. So again, I have these vectors v1 up to vn that are like the eigenvectors for G. I'll erase that aside because I just wanted to use it to mention that part, which I thought it was interesting. Okay, and then I'm going to define, and this is a definition. Um, for the non, I only define this for the non-zero eigenvalues. You'll see why in a moment. So if you have a non-zero eigenvalue, I'll define this vector. I'll define u sub, let me keep calling them u sub k, lambda sub k. Okay, so just to think about what it does, again, like A, again, what is A? A starts in Rn and goes to Rm. So basically, if I take a B sub k, this is where A B sub k lives, right? So this is going to be a vector in Rn, and it's just being conveniently rescaled. That's just like a rescaling, right? So this is a vector in Rm. And you see why I had to assume that you know, that the eigenvalue was non-zero, so that like you can, it has a non-zero square root so that you can divide by it. Okay, why is that kind of like, why is this like an interesting vector? Because it's an eigenvector of H transpose. Okay, so notice that this is an eigenvector. So it's not the same as G, right? Like I'm doing now A times A transpose, right? So again, A was n by n, and A transpose would be n by m. So this would be like, this is an n by n matrix, right? So because like you think, oh, why would you do A transpose times A and not A times A transpose? Like, I mean, those are were kind of like the two obvious choices for producing a square matrix. So what I'm saying is that, oh, actually, this is also related to the other possibility because once you have eigenvectors, for A transpose A, you can kind of like get eigenvectors for A times A transpose. That's kind of like the cool part here. So it's kind of like a bit looks more symmetric now. So, I mean, this is like an easy check because what is A times A transpose U sub K? This would be A times A transpose. What is U sub K is 1 over sigma K A B K. Okay, the pull out the rescaling is 1 over sigma K A transpose A B sub K. Right? But A transpose A is now G. So into A times G V sub K, right? G times V sub K is lambda K. This is an eigenvector for G, right? So this gives you what? it gives you 1/sigma k a lambda k b sub k, right? And then so you get, let's see what I want to do here. Oh, right. Like, oh yeah, we're almost there, right? Because yeah, sorry, like you can get lost in the definitions. So that gives you lambda k. So what we just found is that A times A transpose U sub k equals lambda k over sigma k times A dk, A times dk. But what is A times bk? It is sigma k times uk. Kind of looks like a word salad, but A times bk, or like yeah, A times bk over sigma k is uk, right? So that gives you lambda k times uk, right? But that is precisely like the definition of like an eigenvector, because A times A transpose times uk gives you lambda k times uk. That is an eigenvector. So this is an eigenvector with the exact same eigenvalue, which is so if like I didn't say that explicitly, but in fact these two matrices have the same eigenvalues, which is kind of like interesting, right? Like they so uk with the same eigenvalue that you had for the matrix G, right? The same eigenvalue. This is probably the most proofy possibly nice and let's go. So let's start it with that. But like it's kind of like a fun proof to go over. Like it takes some time to digest, but it's like a kind of like a very elegant proof. So like that's why I wanted to go over it. Um, so in fact, like the eigenvalues, you know, um, as these two matrices have the same eigenvalues, which is kind of like increasing in its own right. Uh, so we're almost done. Because, okay, these gives you a definition. So for each non-zero eigenvalue, you get including repetitions, right? For each non-zero eigenvalue, you have like the corresponding eigenvector. You can produce an eigenvector for the other matrix. And then the idea, just to kind of like finish it off, uh, oh, you can also show, I mean, it's kind of like the same proof, so it's not kind of like maybe worth doing it right now, but you can also show that these eigenvectors are orthonormal as well. So that's why the rescaling is used. So also you can show, it's kind of like the same proof, the similar proof to what I just did. So you can also show that, like the eigenvectors. So just to kind of like repeat what's happening here. So you started with, let me put it in a more symmetric way. You had lambda one greater or equal to lambda two greater or equal to lambda three, up to lambda n greater or equal to 0. Some of these are non-zero eigenvalues, right? Some of these are non-zero eigenvalues. Let's say like let's put the non-zero ones here. So let's say that these are not the non-zero eigenvalues. Okay. So whenever you have the non-zero eigenvalues, you can kind of like pair. You have P1, P2, you have like the corresponding eigenvectors. So these were like the eigenvectors of A transpose A. Okay. And for the non-zero ones, right? For for the non-zero eigenvalues, you can each of these eigenvectors produces a corresponding eigenvalue. Sorry, a corresponding eigenvector, which I'm calling U1, U2, up to U3. Like again, you go like the thing is like this doesn't give you like a definition for like the remaining ones, right? But like the ones that you have in the non-zero case, these are eigenvectors. Of A times A transpose. Okay. Again, this was an n by n matrix. This was an n by n matrix. And then this is an n by n matrix, right? And the non-zero ones are equal to the rank, right? Like the number of non-zero eigenvalues are equal to the rank of A. So these produces eigenvectors for all the non-zero eigenvalues of A times A transpose. So the only thing that is left is the eigenvalue 0. Okay. So this is then you are this is like these are all the repetitions where the eigenvalue equals 0. Because again, like the nullity could be, could be the dimension of the kernel, or the nullity could be greater than 1. So they might, if you include repetitions like that, can be that 0 eigenvalue could appear more than once. So here what you would do is like that's a, you just find like you just extend this basis. If you remember Crash and all these things, you can extend this basis. You find a basis for like the nullity, you know. Um you take a basis for the null space of A transpose A. Sorry, A times A transpose, and you can apply Gram-Schmidt or whatever you want to make it an orthonormal basis. And that doesn't mess up the previous part because it's symmetric. I mean, there's a bunch of things that happen here. But all that I'm saying is that you kind of like extend these eigenvectors, like complete them with eigenvectors which are orthonormal for the null space. Okay. And assemble those into a matrix as well. So basically what's happening, just to kind of like, because we should be almost finished today. So just to summarize what's going on, so what's happening is that you have eigenvectors for A transpose times A. You have eigenvectors for A times A transpose. Okay. And then the matrices that I talked about before is that the following. So let's use these colors. So U would be an M by M matrix. So it's a matrix whose columns are U1, U2, up to UM. Okay. B would be an n by n matrix. Okay. And sigma, so again, this is kind of like thought about each of them as being like column vectors, right? So that it kind of like adds up as columns. And this matrix sigma that I told you about a bit earlier would be six. What did I call them? Did I call them sigma 1, sigma 2, sigma n? So basically, along the main diagonal, I mean, this is not necessarily like, this is not necessarily like a square matrix, but like you kind of like just fill in the kind of like the main diagonal with the singular values. So for example, like just to make it a bit more concrete, if this had been like a 3 by 2 matrix, right? Then like in the case n equals 3, n equals 2, then this would give you what? It would give you sigma 1, sigma 2, right? Because and then 3 by 2. Okay. Or if the matrix had been like n equals 2 and n equals 3, then it would have been like sigma 1. Actually, well, in this case, it also goes up to. I mean, like that last one would be 0. Let's see that. This is how am I setting it up? Oh, I think if I write it this way, I do have to assume that n is greater or equal to n. So, okay, let's do it like that for now. Okay, but okay, let's just finish it off for today. How is it related to the tensor product finally? To see if we have everything in place. Like actually, you don't need to have done this before, but okay. In the last few minutes, just to finish it up. How is this related to the tensor product? So how is this related to the tensor product? What? Okay, so if you want to do A times B, okay? What is A times B? A times B, the B's are a linear combination. The B's are a linear combination of the BI's or the BK's because the BK's are a basis of the space. Okay? Now the way this sum works, right? Only the vectors which are not in the nullity gives you something not interesting. So actually this sum, it goes from 1 to n, but it actually can be truncated up to the rank of the matrix. Because the way I set everything up goes like, like there are some eigenvectors that are eigenvalue 0 and others which are not, right? So you only keep the non-zero eigenvalues. So So you get sigma k, and then A times Vk is lambda k. Oh, actually, this is where, well, let's leave it like this, A times Vk. But now we're only looking at the, no, you know, we are now looking only at the zero eigenvalues, at the non-zero eigenvalues, so you can use that A times Vk equals sigma k times uk. Okay, because remember the definition of uk. uk was A times Vk over sigma k. So I'm just solving for A times Vk there. Okay. Where is this? Where did it have this before? Okay, yes. And then, okay, perfect. So I have the sigma k, I have the uk. So let me rearrange this like this. I'm almost done. I'm probably sorry about that. So I just thought that it didn't make a lot of sense to stop like the proof in the middle and continue it the next time. Okay, but this number sigma k, right? The sigma k arrives when you write V as a linear combination of the bases. If the basis is orthonormal, it's very easy to find the coefficients with an orthonormal basis. They're just like the dot products between the vector and the orthonormal basis. So, but you can write that down as, you know, V transpose, V sub k transpose times E. But you know, it's like a dot product, right? So like these, it's fine, right? So let's replace that here. Oh, this is really fun. About so because this class was a little bit abstract, but now we're getting to the fun part finally. So this is sigma k, uk, and then this is vk transpose, right? Times v. But this is a tensor product. This is uk tensor vk. So this is. So that is what A times V equals to. So it's the same V on both sides of the equation. You erase it out. So erase the V from both sides of the equation, and you get this. Of course, I'll kind of like this, like kind of like redo part of this like next time, so that kind of like a more soft landing. But at least I did want to for you to see, oh, you're expressing the matrix as a sum of tensor products, where the sum goes from 1 up to the rank of the matrix. So that is, you know, and then that makes it clear. Oh, it's actually, you know, the rank is kind of like the same rank as like the tensor. I mean, there's still some minor things that you would need to think through, but that's kind of like the important part. So the singular value decomposition, I'll kind of mention this next time, because I do have to repeat some of this because I feel like maybe I went a little bit fast. But the singular value decomposition kind of like gives you kind of like in a sense and like an optimal tensor product decomposition for the matrix, because these are being set decomposition in terms of orthonormal eigenvectors, where the eigenvectors have like a lot of meaning because they are the eigenvectors of these like A transpose or like A transpose times A. Okay. So again, it's not to worry too much about the proof. Like the proof doesn't matter too much. It's more like what the definitions were. So I'll kind of like do like a summary of the proof next time so that it's clear what matters for us. But and now if you write this in matrix notation, that's how you end up with this formula. You know, if you kind of like go through like the how matrix multiplication works and all of that, like ends up being equivalent to that decomposition. But for our purposes, because I wanted to run it this way with tensor products, that's why it's more useful to see it that way. Okay, let's finish here. And sorry, if I went too fast, I'll kind of like repeat you next time, what you need to know.
I have a quick question.
Yes.
So for the homework,